And welcome. We're going to explain what I've been doing, building this synthesizer. I'll go around the board here and explain what is on the board and what components are doing what. In this instance, we're talking about digital synthesis using Arduinos. Basically what happens is all the Arduinos have a pulse width modulation I/O, PWM, they short term from it. Basically you're talking about a clock, a digital clock that counts up and reaches the top, it falls over and goes back to zero and goes back up again. Then what happens is generally, get a marker here, so you've got this PMW here, which is counts up to tick, 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 like this, and then falls off, and then goes up again like this. You're taking these digital values and you're placing them through a digital to analog converter, and you're approximating analog voltages. You can set the duty cycle for how the frequency of these, the duty cycle for how many volts you want these to go through, and basically all these synthesizers work the same. I'm using multiple synthesizers here in this project. I've got a Arduino Mega 2560 here. I've got an Uno here, and I've got two Mega 328s here. I'll explain those in a minute and why I've done it like this. But we'll talk about this one first. This came from a project from Peter Knight a few years ago, who created a digital synthesizer using basically grain filters and with Decay, and a pair of them, and a frequency pot to control tone and or frequency. Other people have turned them into, in this particular case, I've got the oscillators here, and I've got an 8-channel or 8-point sequencer, which stores tones and can play them back in various orders I want. This is eventually going to become a 16-point sequencer. Right now I've only got 4 switches because these are the only ones I had that would fit this particular board, and I'm using 8 LEDs, but it's easy to convert this with this board to 16. This board here gives me 32 digital I/O, 16 analog I/O, and another 16 pulse width modulation I/O. It's all digital I/O in the essence of it, but they're treated very much like between analog, digital, and pulse width modulation. On this board I've also got a tempo and a pitch. I've tuned my synthesizer to be basically diatonic, in the sense that I'm using a key of D here for 10 different keys, and then I've got 3 keys over here, each one run by a different synthesizer or different Arduinos controlling each one independently. And I wanted independence because timing between the chips is not always the same, and you can overload these with doing too many tasks in these loops with what you're doing. I'm going to put the source code and everything else online with the links. I'm not going to give you the source code for what I did here, because you can rebuild this whole thing, and with your own imagination you can go into doing or replicating or even expanding and coming up with something else. I'm just going to go back over here. Over here I've got a Reverb Decay echo unit. You can find these things here from any guitar shop. There's so many of these from broken bits and pieces of stomp boxes that come around. It's using a PT2399 chip. If you look that up, I'll write it here, PT2399. You Google that, and you will come up with a dozen circuits for using Decay and Reverb and special effects to give yourself more presence in your sound other than these little toy sounds. Like I say, the links will be all included on this video at the bottom. You can just happily go peruse them and change these and modify them. The code itself fits on about 2,500 bytes of code to run the Arduino Mega, because you're running the sequencer and the oscillators. The independent ones over here, and I'll just jump into here. This is a Uno, and these guys here, there's 2 of them here. They are about this big. This is a Adafruit version called the Trinket. You can get the Arduino Pro Minis. You get them on eBay. They're $1.98 a piece. They require a different driver than the other ones. You basically program them. They're exactly the same functionally as the Uno. However, process-wise or workflow-wise, these have a lot more going for them. These are basically, you program them, you need a separate USB programmer because these do not have USB. They have the exact same pins as the Uno does. Input output, the exact same processor, the exact same RAM, everything's identical, except this comes with onboard power, it comes with actual power controller, it comes with USB. These strictly just come with the microprocessor and the reset, and all the pins are solderable on these, where these they've got these great type plug-in pin buses that you can use. So I'll get started. I'll start with my small keypad over here. I'm again running a pair of oscillators, one fine and one gross. It's basically a 2 grain and then a decay against the grain. All three are sharing these oscillators because I'm using the one common sound to come through here. Each one of these is programmed in a different key. And I've programmed my pad here to go key of D, key of A, and key of D. So I base this on the Merlin or the dulcimer stick, the stick dulcimer, 3 strings. It's pretty hard. Pretty hard to make it not sound bad. Everything's running through my reverb, my delay box over here, so I can show you. We can change some pitch here. These here can be anything that causes a resistance of, these are about 10K resistors. You really only need 5 to 10 kilo ohm resistors on any Arduino. They simply don't have the large impedance draw that you're going to need anything more. You might need resistors to place resistors between the wiper and the ground, or between the wiper and the power in series, because you're going to get some noise. No two pots are the same, and these are very different. Although they're linear, and the same with these potentiometers, they handle the sound and the noise very differently. So extra capacitance and trimming on all your pots is going to be required to make this give up some of the really crappy noise and toy sounding noise for something that sounds more like real analog synthesizer. Over to my sequencer, I'm going to start this. You basically, the concept is you hit a, and again I can turn the notes up the scale. And I'll put another one in here. And let's make something really funky here. And again, I can change the entire pitch, again, using the same diatonic scale that everything's running on. Although that one actually makes it go flat. Unless we can really have some fun here. So notice turning the delays and decays off and the echoes off. You get very, very different sounds with these. This is just short circuiting actually two of the leads on the IC over there. Back. One more thing about this is that normally on a guitar or a stringed instrument, you'd strum it, this would be open. With a synthesizer, you can't do that. So open chord, so that's open D, open A, open D. You have to remember that because you're not strumming. So, I've now got to get this, and my concept here for the entire instrument was to build it into something that was small, that was attractive, and that wanted people to pick it up and play with it, a new kind of instrument. And I thought about different packaging and different boxes. And then I thought of something really cool. Could I get all this into an old, unused violin? And I shopped around, and people want a lot of money for used violins, but I found something really cool. I found a fiddle kit. Someone had started building their own fiddle, and it's already opened up, so I can sit here and get all this into here. And the concept is that I would put my electronics on a pan. I've still got to get a couple circuit boards made. I'm just going to use hardwired circuit boards, hand done. Put the pan inside the box like this. Put my lid on here and get these potentiometers and switches. Switches would be nicely put in here. The potentiometers would be strategically located here. My LEDs and buttons would run down here. And then I want to take this, and I want to put these guys on this so that you could literally play it. Play the violin like this. And something like that would be a really cool idea to pick up and just for something to do it. The problem I'm going to have is that these pots are a little too wide. And just peel some tape up here. You can see the actual ribbon that you touch is actually narrow enough, but the rest of it's all tape. It's basically you peel them off and they'll stick, and they will stick really, once you're going to get them on something, they're hardly going to come off. So I phoned the manufacturer and they said they don't recommend it, it's going to void the warranty, but a lot of their customers do it, which means, yeah, go ahead, it'll work. Some of the other things I might change is that I'm going to be building fully analog oscillators and a sequencer and another oscillator over here, and I want to come back to another video and just show the difference between what digital synthesis versus digital synthesizers versus completely analog synthesizers do. You can go back and you can actually get the schematics online from the original Moog or Buchla synthesizers. The difference being is all this stuff, all of it runs on 5 volts. Even the stomp pads, they take a 9-volt battery, but all you got to do is pull the regulator off with maybe the capacitor, and you'll look online and they're all putting out 5 volts. So they're powering the board by 5 volts, even though they're using a 9-volt battery. So 5 volts, 5 volts, 5 volts is a single power line. You're going to find that in analog synthesizers, most of them are bipolar. In other words, they require a both positive and negative power supply, anywhere between 12 to 15 volts, plus and minus 15 volts, plus a ground. When you're doing this way, you're going to have at least 2 different kinds of grounds. You're going to have an analog ground, which the analog ports and your controls and everything else should use, plus your digital. And you want to keep your digital grounds and your analog grounds separate. They're grounded in here, but they use decoupling capacitors back and around here to actually keep noise transients from going between the analog and the digital channels. Sometimes you're going to have to put the coupling capacitors between the Arduino and the power as close as you can. I use these 0.1 microfarad Mylar guys here. They're great. You're going to have to do this because you're going to get a lot of noise and a lot of hum. And even on these things, you're going to get, you'll see that it starts to pick up a transient, and they'll take over and they'll keep going forever. You can do that again by trying to put anywhere between a 1 and 10K, oh, this is a 5K pot, so a 1 and 5K resistor between the signal or the wiper and the ground, or you might want to throw in another capacitor just to take up some of the slack, because these things are up 10%, so they can actually go over 5%. And because the math on the algorithm in the software is doing one thing, your theoretical here doesn't match the physical manufacturing of these, and so you're going to have to do some tweaking. Anyway, thanks for dropping by, and if you got any questions, please, my email's on the video, and look at the links and go and try to build these. Again, these Megas, you might want to start off by buying a real Mega or a certified Arduino one. Shipped to your door, they'll run between $35 to $45. I shop eBay, I shop China. The Arduinos I'm buying for, the Unos I'm paying $3 for, the Pro Minis I'm paying $1.98 for, and the copy of the Megas I also use, I pay probably about $4 for. And they're okay to blow up. You're going to be blowing these up because it's just the nature of the beast. But keep these guys around because you'll know they work. These require a special driver that doesn't work with the Arduino IDE. Again, shop online. I'll put links up if I can. If you leave a comment on the video and you really, really want to, I'll do that. Anyway, have fun synthesizing. Thank you.